Greetings. It's a pleasure to be back. Last time I was here, it was 2 years ago, and I was talking about invading IPv6 for the dual stack protocol implementations. Now 2 years have passed, and the tool that I described to you 2 years ago is now a fully functional tool framework where you can invade the intrusion detection system's network bypass, so for information exfiltration. Currently what I'm doing is the research on IPv6 protocol stack. And my main goal is, and it's about the presentation, you will see, and my main goal is about to find the vulnerabilities within the kernel implementations of the protocol stacks. Now, I'm a member of CERT.LV, and I'm a senior researcher at NATO Cooperative Cyber Defense Center of Excellence. I'm doing a lot of research and red teaming and exercise development, and this is one of the things that I also do there. And besides, this is also the topic for my PhD research at the Tallinn Technical University. So, let's carry on. And when I gave in this presentation, I had the idea about either to make this a really, really technical presentation, like dumping codes of kernel on you and providing you the core dumps of the memory and trying to overflow you. But then I thought, well, I'm running out of time. Firstly, because this project started like 1 month ago, and thought, okay, what else? I can draw my own slides. So bear with me, these are my own drawn slides. There's 18 of them. So it's number 2 now, so it should not take too much time. Now about the Linux. I start off with the Linux, with the penguins. Now they are everywhere. Even though the corporate environments might use Windows as the primary operating system for everything they do, nevertheless, there's always a specific need where a BSD-flavored operating system or Unix derivative or Linux distribution would be the one that fits the most. So Linux is being very, very efficient in tailoring and adapting to whatever needs you require. For example, you can create a microkernel that will run on the programmable logical controller on the PLC that runs a factory. You can have a Linux modified that runs on your smartphones, such as Android uses a customized Linux kernel, and then they add on top of it their additional features. So penguins are around us. Now, I think it was 2 weeks ago when Krebs on Security on his blog post reported about a denial of service attack about 1 terabyte per second. It's a massive, massive denial of service attack. And he claimed that this comes from the Internet of Things. Now, this is a sales word, Internet of Things and Internet of Everything. Nevertheless, the idea was that the devices got compromised. Now, according to Krebs on security, the devices didn't get compromised because they were running, I don't know, a weak patch levels or the kernel was exploitable. No, they were exploitable because they were misconfigured or they were running the default configurations. If that's, for example, a Wi-Fi router that runs a DDRVT, it might have just a default password. So we are living in the age where we, as the admins, we are deciding what fits our use cases the most. Now, why have picked the Linux instead of Microsoft? And believe me, the Microsoft is the next in line for me to do the research. I have it already deployed in the lab. Linux is a bit easier since it's open sourced. And I'll cover the core ideas of that. Now, why do we want to target the Linux kernel, or why do we want to target kernel at all? It's a trend now, even though targeting the core is not that anything new. It's not brand new. It hasn't been invented like in the past 2 years. Now, targeting the core has been already out there for ages. Whenever the first rootkits were established, they wanted to invade in the dark corners of the operating system. So they had to understand how the kernel is working, how the dispatch is doing, how the interrupts are being assigned, how the task switching is being done, how the context switching is being done, in order to try to evade and stay unhidden there on the network. Now, attacking the core is a game game of a chess, and we are playing chess here in this conference as well. Whoever is controlling the core, obviously controlling the kernel, is controlling how the operating system functions. Now, don't get me wrong, targeting the core is really, really tough. It's not that easy. In my research, I'm trying to do as a remote attacker. I'm not trying to do a local attacks, such as local privilege escalation, or something that will give me an elevated privileges. I'm trying to do it remotely. Why remotely? Because it is more fun, it is more tough, and it's more harder to execute such an attacks. But the results are way, way devastating. Now let me bring you into the user land and kernel land. Now, these two lands depends on the memory that is being used, the memory segmentation model being used on the current CPU that you are using. However, on the Intel compatible ones, the user land and kernel land are segmented. So on 64-bit architecture or 32-bit architecture, there are two main lands. Right, there's a kernel space, which represents everything, the all core functionality that is required for the operating system to function, and for the tasks that are being executed by the user to be executed properly. Now, in the user land, this is where we run our tasks. And on Linux, by task, I mean any application that you run. Any fork process, any clone process, everything is called as a task. Now, on 32-bit systems, on a typical operating system, the virtual memory that is assigned for a task is split into two halves. On Linux systems, altogether it's 4 gigs. Out of that, 3 gigs is assigned to the user space, and 1 gig is assigned to the kernel space. Now, in these 3 gigabytes, this is where the user application, such as executable code, is being run. All the data that is required for the application to run is being stored. This is where the stack is stored. This is where the heap is located as well. This is for the user land. Now, kernel land being smaller, accordingly, to the 4 gigs, unless there's a higher extensions being used. It also has its own heap, it also has its own stack, it has its code segment. However, in the kernel land, since the kernel land is being used by all the tasks that are running there on your computer, all the tasks share the same kernel. Meaning that if we get a compromise of the kernel from the one task, we potentially can compromise the others. Maybe you have heard about the race conditions. Now, the race conditions exist. And race conditions exist especially in the kernel mode, where the tasks might be racing in order to get the lock or in order to start their own execution. In that case, if there's a race condition exists or an attacker can exploit it, an attacker can redirect a functional task to the malicious task. Or if the race condition fails, a deadlock might incur, meaning that the deadlock means the computer has hanged. Now, this picture also represents the defense mechanisms. Let me talk about the defense mechanisms about the kernel space. Now, defense is typically organized most commonly in 3 general categories. Now, it's a hardware-based. Whatever your hardware, your CPU is providing, such as DEP, which is data execution prevention, and it's either the non-execute or execute disabled bit set either by Intel or by AMD architecture. So this is where the pages of the memory are marked as read-only, meaning that if the attacker gets control over this memory area and is able to write the code there, it will not be possible to execute unless there are other ways how to make this page executable again. Now, hardware provides a lot of features, and the recent additions, which are currently still under research by Intel, introduce a lot of new technology, new chips that will control how the flow of the data and how the program execution goes, but not at the software level, but at the hardware level, in order to stop the attacks already at the hardware level. Now, it is going to be very, very tough to circumvent those. Now, we have also software-based. So software-based, and it's either on the Windows systems, maybe you have heard, if you are doing the Windows exploit research or exploit development for Windows, there is safe SEH, or SEH, which is safe exception handler, which is pretty much just a chain of try and else. What happens? Try this, and if it fails, go to this handling procedure. This is not a true, non-executable stack or memory. However, that is already something that's provided by the software itself, such as operating system. And there are compiler-based options. That stands for the CMP, by the way. In compiler, this is when you compile your code. If you are using GCC, you can use specific flags in order to compile your code. If you're using a C# to develop stuff on the Windows system, you can provide specific flags how to enforce specific security mechanisms on your application. Now, compiler-based would be stack canaries, or stack cookies, or heap canaries. These are the fields that protect the metadata to be not to be overwritten in case of the buffer overflow or in case of the heap-based overflows. There is address space layout randomization, ASLR. This is where, instead of having a static memory assignments in the memory, they are being randomized upon every time, every execution. Why it is critical and why it is hard to circumvent? It's critical because if the memory is static and all the memory address locations are static, an attacker can learn those static addresses and use to its benefit. Now, when the randomization is in place, an attacker has no clue where his shellcode might be located. However, it depends also on the ASLR implementation. It depends on the entropy of how many bits are being used in order to randomize the address. Now, all of these are also valid for the user land and kernel land. These mitigations are the ones that need to be circumvented in order to execute your payload. In kernel land, well, there are additional ones such as red zoning, where you are limiting specific areas not to be overwritten. You're implementing guard pages, it meaning that if there is something written to this guard page or this location in the memory, it is going to be terminated. The execution is going to be halted and the kernel panic will be raised. Now, userland is bigger, and userland has different tasks to be run there. However, we can place there many security mitigations as reasonable it is. However, if we are bringing the security mitigations to the kernel land, and we are introducing new security mitigations and checks every single processor time, on every CPU time, it means that the computer will get slower. It means that it needs to have yet another security to be checked. It needs to verify if this specific application is still running functionality, is there, and the integrity is correct. Now, kernel land in this sense is a little bit less protected, but is more complex. It's more complex, meaning that if a malicious payload goes into the kernel land, it has more chance to mess up stuff. And if it is messed up in the kernel land, it will mess up the whole computer. I mean, it will mess up the whole running kernel state. It will go to the blue screen of death on the Windows, or it will raise a kernel panic on the Linux systems. Now, targeting the kernel, we have different ways. This depends on the inputs that are provided. And now on the inputs, meaning that in the kernel, a user can provide its own request for the kernel to be processed. So if it's from the inputs from the user land, or there could be inputs provided also directly into the kernel, such as a packet, such as a TCP/IP based packet that will be arriving there at the kernel. And now the fun starts about how do we invade this, how do we use it. So my priority is there, I'm doing this as a remote attacker. So I'm sending in an IPv6 packet, and I'm going to describe about what is the approach, what's the methodology I'm using. However, the invading the kernel is not that easy and straightforward. There are at least 3 conditions that can be triggered. One being the denial of service, which is fairly simple, maybe, in some cases, just computer crashes. However, we just cannot say that denial of service is a lame attack. Sometimes, when there is a critical services running and it's vulnerable to denial of service attack, and you're able to take down this service, it might be inflicting huge damage on the provider, or it might be on the users that depend on this service. Now, information disclosure. This is also a way that can be how the kernel can be attacked. We can attack the kernel in a way that it will try to disclose the information that we can craft for our upcoming new attacks. Or code execution. If we get really, really lucky, or some magic happens, we get blessed by a fairy or a tooth fairy, and it gives us 3 wishes, and we can say, I want a code execution in the current state of the kernel, then it might be an option. Now, kernel is being developed by many developers and way more contributors, meaning that it's really tedious task for those guys who are keeping up the kernel. I mean, they're doing really good job. They're doing really well. And kernel development is based typically on the guys who are developing the kernel. So new additions to the kernel depend on the developers and the contributors if they're able to bring in this thing. You need new support for new hardware. Either you code it on your own, or you wait until it's being implemented by the kernel, or somebody else has provided a loadable kernel module. Now, kernel development, even though it is a very beautiful thing, it's very chaotic, even though it's being organized, and they try to do the best there is. We have to think about how the kernel is being developed and how the new things are being added. Now, I'm here talking about the dual stack host. This is dual stack host means that the kernel supports both the IPv4 and IPv6 hosts, IPv6 addresses at the same time, meaning that's even an additional attack vector. The IPv6, even though it's called the new standard, it's been already there out from 1998 and brings in a lot of different headache. I mean, the system administrators are now facing the new challenge about restricting their networks, understanding their networks on the field of the IPv6. How many of you are monitoring your network for IPv6 traffic? A raise of hands? No? Some, okay. Well, you always monitor your traffic, I know. Now, IPv6 is still not well understood, even though there is a lot of material, there's a lot of training. We know how to secure our networks from the IPv4. We know how to implement firewall rules on the IPv4. However, sometimes we forget to implement IPv6 rules. We really forget. Now, when I was doing the research, as I mentioned previously, the research about evading the network traffic detection systems in NIDS, how can I craft a packet that will evade it? Now, actually, crafting is fairly simple, and the tools are available on my GitHub page, and you can download and test your systems. But when we talked with the vendors that we tested, and we said, hey, your awesome tool doesn't support IPv6, why is that? They said, oh, the customers do not request IPv6, so we don't care about it. Now, with an open source community, it's a bit different. Now, with an open source community, it is that even the detection software, sometimes you might see that it supports IPv6 or it doesn't support IPv6 at all. For example, a really good example is Moloch. Moloch is a really awesome tool for network monitoring. Now, before this year's March or February, it didn't support IPv6 at all. Now there is a better version that supports IPv6, and now you can have a better visibility on the network for incident handling. Now, Bro is a totally different story. Bro is where you are the one who detects the incidents on the network, so it supports everything. Now, with the dual stack, layer 3, the IP layer, is where there's one part responsible for handling IPv4 packets, the other one is for handling IPv6 packets. Now, the attack surface is increasing, and we have more ways to attack this thing. So how do we attack these hosts? There's I at least take 3 approaches. I try to figure out the known attacks, looking at the history, looking at the current trends, what are there for kernel attacks. The second one is the source code analysis, and the third one is the fuzz testing. Now, about the known attacks, there's a plenty of known attacks from the history about the kernel. However, the most recent one, and it was in a Usenix conference this year, maybe somebody already read the news in August. In Usenix conference, there was an off-path TCP kernel attack. What it means that the attacker can get the information disclosure. This is by predicting the TCP sequence numbers, and it allows to inject malicious payload, malicious data into this session. Now, the kernel versions vulnerable to this off-path TCP attack are from kernel 3.6 to kernel 4.6. Now, the current latest version of the kernel is 4.8, and it also depends on the operating system, on the Linux distribution that you're using. Debian stable uses the stable version of 3.16, I guess, which is fairly old but stable. And if you're running the production environment, you always rely on stable stuff. And for example, Arch Linux uses the most recent 4.7, not the release candidate 4.8. So there's a lot of known attacks, and ways how to attack them are also known and released in the public. The second part is the source code analysis. Now, it's a huge, huge library. It's a massive, massive pile of source code written in C. Now, digging through, and I've been partially already gone through most of the code that is responsible for handling IPv6 input traffic. Now, it's still a very tedious task. There are two ways how you can do the source code analysis. There's either you rely on the automated tools, such as RATS on the Linux systems, which pretty much just what it does, it just looks at the source code and tries to figure out if you're using a bad function there, such as getS, for example, that doesn't do the bounds checking, for example. And there are commercial tools out there, such as Fortify from the HP, which will have additional logic in there in order to figure out if your code is okay or not. And the second option is, well, where you as the human, you as your own intelligent being, you're trying to read the source code and trying to figure out where you can attack this piece of code in order to get the leverage. Now, there are pros and cons for both ways. However, the exploit developers, they say, yes, use the source. The source code is where you will find most likely the vulnerabilities. This is where you can see off-by-one coding errors. This is where you can see null page references. This is where you can see race conditions. So source code is a very tedious task. Source code analysis is a tedious task, but it really, really pays off. Now, I'm not sure if everybody's able to see this. This is just an excerpt from one C file. And the point that I want to stress there is the red one, and it says the IPv6 input is based on Linux net IPv4 input, meaning that the developers, they took the working IPv4 protocol stack implementation and they just adapted it to meet the requirements for the IPv6. Now, I will not go deeper into this. There's a lot of stuff in the source code. I have to cover a lot of ground here, so I will not go deeper into this. The third part is the fuzzing of the kernel, meaning that you're providing random inputs. You're sending packets that are random totally, or they are according to the specific case, and you're defining your use cases, but you're trying to break the target by providing it with an unexpected input. And maybe this unexpected input will trigger either a denial of service condition, maybe it will trigger the information disclosure, or maybe it can later turn into remote code execution, which is like awesome. Now, fuzzing the target, there are so many different frameworks available. There's AFL fuzz, even though this is not a network protocol fuzzer, it's a file-based fuzzer, but you can try to shim it in order to fuzz a valid IPv6 packet and then provide it and send it over the network. Spike is one of the early implementations. It's a really, really great tool. However, it's very complex to write the test cases. This is where the Sully came in. Sully was the one that took the best parts of the Spike, and they said, let's simple this down and ease the development of the test cases. Sully was, I don't know, it's not maintained too well already for some time. However, the next incarnation of Sully was the Fuzz. Fuzz is a really awesome framework which is based on Sully. I've been working together with the developer in order to expand it, in order to implement that further. There are others, such as Peach, which is, has its community, and the paid version. There are a lot of things out there. However, I decided that for what I need for the binary protocol fuzzing, there's no support for it in the open source yet. So I said, screw it, I'm going to write my own tool that will do the binary fuzzing that I want. Because either I have to fix the code for the other implementations or I just create my own. Now, I came up with a simple approach. I only have 3 or 4 stages. The first stage is where you select the layer. The layer being the protocol TCP/IP or OSI 7 protocol stack layer where you want to start off. So if you want to create an Ethernet frame, you start off with the layer 2. If you want to already start from the layer 3 with IP protocol already in place, go from there. You want to start from the transport layer, fine. You just select. This is where the framework meets the requirements of the developer or the requirements of the security tester. So you start by selecting which layer you want to go off. After you have selected the layer, you want to describe the remainder of the payload. So the payload has, if you are starting with an Ethernet packet, you have to describe all the upper layers. So you have to describe also the IP layer, if that's the case for fuzzing the IPv6. Then you decide all the protocol fields. If there are extension headers in use, then you have to specify all the extension headers, which is a really, really tedious task. However, I tried to make the protocol assembly as simple as possible. This is where you are deciding where goes what. So is this field fuzzable? Is this field static? Is this field going to be mutated, and how it is going to be mutated? Once you have selected the payload, you have to decide on the cases how it is going to be mutated. And there is a mutation engine. I thought maybe there is some already mutation engine out there that can manipulate the binary traffic, and there is, to my best knowledge, I couldn't find one, so I have to write my own. So mutation engine, you provide a valid test case, and it will mutate according to what you have described. So either in the binary protocol, it will do the bit flipping, bit shifting, it will do the random injection, so there's a lot of things. So and the mutation engine has to also have an idea of grouping. So you have to have groups of valid sequences. For example, if you are targeting multiple paths and on the protocol execution, you need to have a specific groups of the valid values so that the packet that you send doesn't get dropped by the kernel, but it's accepted by the kernel and processed by the kernel. Now this brings us to the code coverage. The code coverage, it's software engineering. I really hate software engineering, but I have to break my mind into software engineering in order to ensure that the code coverage is correct. Why the code coverage is important? Because the IPv6 protocol stack implementation is really huge. And if I do not take the correct path, I might not reach the buggy part. I might not hit the bug. So if you see in the picture, there are multiple paths. And I might go into the forest, I might stumble upon a bear that was not good, but I want to find the treasure, or I want to go to invade the castle. So code coverage is really important. So once we have these 3 pieces together, we have decided upon which is the starting layer. We have described the test case for the remainder of the payload. It's being fuzzed. The fuzz test cases are stored on the fuzzing stack. So this is where all the fuzz cases are being located. We try to fuzz it. We send the fuzzing test cases to the target when we need to monitor how the target behaves. Either the target crashes. If there is a crash, what is the crash? If it's, I don't know, if it has a core dump, then we have to figure out which crash condition, the test condition, was the one to cause the crash in order to collect the core dump, K-core dump, in order to analyze what's there. So it's very, very critical in order to monitor the target, in order to verify that your attack or your fuzzing is really, really successful. Now, way ahead, I've just started. Currently in a huge cyber range with a lot of resources. I have deployed multiple Windows editions, starting from Windows 7, Windows 8, 8.1, and Windows 10. I have different distros of the Linux. So these are the ones that are currently being there as the target systems. I'm developing the fuzzing framework. However, the way ahead is really, really far. There's a lot of things to be done. Now, this is my final slide, and it's slide number 18. Whatever you do, the truth is in the kernel, and I'm now open for the questions.
Okay, I don't see any hands raising, so because we are a bit late, let's skip the questions until the coffee break. Thank you for your really educational content and fantastic slides.
Okay, thank you.